Volcanoes have long fascinated mankind. They can be considered as the Earth's geological architects. They have created more than 80% of our planet's surface, laying the foundation that has allowed life to thrive. This video aims to address questions such as, how did the Canary Islands and other similar volcanic islands form and evolve, and what is their eventual fate? Why are La Palma and El Hierro still active, while other Canary Islands have not seen eruptions for thousands of years, or much longer? We will also touch on terms that may be familiar to many from films and TV, such as the Ring of Fire and the San Andreas Fault. In order to understand the answers to these questions, we need first to look at the makeup of the Earth's inner structure in order to appreciate the behaviour of plate tectonics and volcanoes. We can then move on to look at volcano and island formation and the differences between the islands. The Earth is made up of three different layers: the crust, where we live, the mantle and the core. Each layer has a unique chemical composition and physical state and can impact life on Earth's surface. The core is the centre of the Earth and is made up of two parts: the liquid outer core and the solid inner core. The outer core is made of nickel, iron and molten rock. Temperatures here are up to 5,500 Celsius. The liquid mixture has a low viscosity and is subject to violent convection currents. These create and sustain the Earth's magnetic field, for which we can be very grateful, as it safely deflects most of the dangerous high-energy charged cosmic radiation back into space before it can enter our atmosphere. The inner core is a hot, dense ball of mostly iron, with a temperature of around 5,000 degrees Celsius, well above its melting point. However, because the pressure at these depths is nearly 3.6 million atmospheres, the iron remains in a solid state. The crust is the outside layer of the Earth and is made of solid rock, mostly basalt and granite. The mantle lies above the outer core and is essentially hot rock composed mainly of oxides of silicon and magnesium. The crust and the upper part of the mantle is known as the lithosphere and is broken into tectonic plates, both large and small. The lithosphere rests on a mantle layer known as the asthenosphere, which is at a higher temperature. While this layer is solid, it behaves plastically and is able to flow. This is one of the reasons for the movement of the tectonic plates sitting above it. There are two types of crust: oceanic and continental. Oceanic crust is denser and thinner and mainly composed of basalt. Continental crust is less dense, thicker and mainly composed of granite. Magma, or molten rock, originates in the lithosphere and asthenosphere and is released onto the surface as lava from volcanic openings in the crust. Magma formation is complex, but is essentially dependent upon factors such as temperature, pressure, chemical composition and structural formations in the mantle and crust. Let's now have a look at plate tectonics, or the interaction of the slabs or plates that make up the lithosphere. This is what the continents are made of, and where the water in the oceans sit on. The surface of the Earth is divided into 7 major and 8 minor plates. The largest plates are the Antarctic, Eurasian and North American plates. Most volcanic and earthquake activity occurs at moving tectonic plate boundaries, but also within a plate, as in the case of the Canary and Hawaiian Islands. Plates move slowly, typically by 1 meter every 40 years. They can either separate from one another, slide along each other, or collide, with one subducting under the other. An example of separation is visible on Iceland, where the North American and Eurasian plates are pulling apart, allowing magma to rise via volcanoes. A sliding example is the San Andreas Fault in California, which has been the subject of many films. This is an interaction between the Pacific and North American plates and is responsible for the earthquake activity in that area. An example of colliding plates is the subduction of the denser Pacific Oceanic plate under the less dense continental North American plate that caused the massive earthquake and tsunami in Japan in 2011. Mount Etna in Sicily, which erupts frequently, is formed by the subduction of the African plate under the Eurasian plate. Melting of the subducted plate causes an increase in pressure and temperature, which leads to the formation of a molten rock or magma chamber, which can then erupt to the surface as a volcano. While we are discussing tectonic plates, many people have heard of the Ring of Fire. The Ring of Fire is a string of volcanoes and sites of seismic activity around the boundaries of the massive Pacific plate and other less dense plates. Roughly 90% of all earthquakes occur along the Ring of Fire, and the ring is dotted with 75% of all active volcanoes on Earth. However, not all volcanoes are related to subduction. Another way volcanoes can form is what's known as hotspot volcanism. In this situation, a magma hotspot in the middle of a tectonic plate can push up through the crust to form a volcano. Although the hotspot itself is thought to be largely stationary, the tectonic plates continue their slow march, building a line of volcanoes or islands on the surface. This mechanism is thought to be behind the Canarian and Hawaiian volcanic chains. The Canary Islands sit on the African plate, which has moved slowly eastwards, taking older islands with it. The ages of the main islands range from around 1 million to 2 million years for El Hierro and La Palma in the west, to around 20 million years in the east for the Lanzarote and Fuerteventura chain. It should be noted that although the hotspot theory is the consensus view, it does not fully explain everything, and other hybrid theories have been proposed. So how does a typical volcano form above sea level? The majority of volcanoes are cone-shaped mountains. They are formed of alternating layers of lava and ash from multiple eruptions. Very hot magma, which is molten rock with dissolved gases, flows up under pressure through vents and fissures in the crust. As the pressure decreases, the dissolved gases are released, resulting in the volcano erupting. The magma is ejected as lava flows down the slopes and as ash clouds of fine volcanic rock. In more violent eruptions, pyroclastic flows can also flow rapidly down the slopes. These are a mixture of very hot rock fragments, ash and gases. The flows surge along like a boiling cloud and is one of the biggest dangers to life near violent eruptions. Eventually these form a layer of ash on top of the solidified lava. This process is repeated each time the volcano erupts, and the resultant interlaying forms what is known as a composite or stratovolcano, such as Mount Teide in Tenerife, Mount Etna in Sicily, and Mount Fuji in Japan. So what are the main visual geographical differences between each of the Canary Islands, and how is that related to their evolution? All the 7 main Canary Islands originated as separate submarine seamount volcanoes on the floor of the Atlantic Ocean. Each seamount, built up by the eruption of many lava flows, eventually emerged as an island many millions of years later. Volcanic eruptions continued at each island to build up the land masses. Because of the relatively deep ocean, the submerged volumes of the islands are actually much greater than the emerged visible parts. The westerly islands have high peaks, and over geological timescales, natural erosional and sedimentary processes have shaped a rugged mountainous topography with dramatic coastlines. Furthermore, the high average elevations have allowed cloud formation and rain from the prevailing trade winds, which has resulted in regions that are rich in vegetation. In La Palma, the best example is the majestic Caldera Tabirente, which is an immense depression, one of the largest in the world of its kind. It is a rich green environment with an abundance of plant life, and is full of deep ravines and steep escarpments surrounded by peaks of up to 2,400 meters high. As the 2 youngest islands of La Palma and El Hierro are still located over the Canarian hotspot, they are still very volcanically active. Here we see the Cumbre Vieja ridge in the south, which contains a number of volcano cones that have erupted frequently in the last few centuries, with the most recent example of course last year in 2021. In contrast, La Gomera has been inactive for around 4 million years, and this is reflected in the topography, which does not look obviously volcanic, is very green, with a rainforest in the centre at an elevation of some 1,500 meters. It contains enormous spectacular radial ravines and valleys that have formed from the uninterrupted erosional processes over the last 4 million years. The erosion has also exposed rock sequences that would have remained buried in more active islands, such as these, which are the remnants of solidified magma in a fissure vent. Tenerife and Gran Canaria have undergone significant erosional processes and have a diverse elevated topography, with arid volcanic regions, forests, deep ravines and valleys. Tenerife, of course, is dominated by the 3,700 meter Teide volcano and caldera. While these islands are no longer over the Canarian hotspot, occasional smaller eruptions can still occur many millions of years into the erosional period, due to complex processes associated with gravitational compression, rebounding and fracturing of the weakened oceanic crust underneath the islands. These changes can then produce conditions for new magma to form and eventually be released as lava in smaller eruptions. The last known eruption on Gran Canaria was around 1,000 years ago, while Tenerife has had minor ones in the recent centuries on the Teide caldera. In complete contrast to the westerly islands, the eastern and oldest islands of Fuerteventura and Lanzarote are very arid and have relatively subdued topography due to calmer initial eruptions during their formation and due to the significant ensuing erosion over many millions of years. While Fuerteventura is around 20 million years old, Lanzarote is actually only around 15 million years old, because it emerged much later despite the submerged parts being connected and being of similar age. Due to their proximity to the African continent and lack of elevation, there is little rainfall and vegetation. Fuerteventura has had no recent volcanic eruptions and has a desert-like interior with heavily eroded topography. It has a large coastline full of attractive golden beaches, which were formed from natural sedimentary and erosional processes. In contrast, Lanzarote has had recent eruptions, most notably in 1730 to 1736, in the area now known as Timanfaya National Park. Thus, large parts of it are covered with relatively fresh lava, and many dormant cone volcanoes are visible. The landscape is dominated by deeply eroded volcanic massifs with U-shaped barrancos and high vertical cliffs. These are separated by a wide central plain covered with organic sands. What is the eventual fate of volcanic islands? Well, the simple answer is that in time they submerge due to erosion and due to subsidence of the oceanic crust on which they sit. However, the Canary Islands are much older than, say, the Hawaiian volcanic islands, the oldest of which is only 5 million years old. The older ones have long since become submerged due to subsidence of the relatively thin oceanic crust of the Pacific plate on which they are located. One of the main reasons that the Canaries remain immerged is that the oceanic crust on which they are located has a low subsidence rate, due to being relatively strong and thick from the continual sedimentation from the African continent. If this were not the case, then all the islands except El Hierro and La Palma would have submerged millions of years ago, and none of us would have ever gone to Tenerife or Lanzarote on holiday. Fortunately, complete submersion will not happen for many millions of years, allowing us and future generations plenty more visiting opportunities.